mean, here you have three variables, right? You can write down starting at x3, condition x1 given x3, and the last term here, right, will be, notice that p of x1, x2, x3 is p of x3. This is in general true. x1 given x3, right, times p of x2 given x1 and x3, right? That's the, always true by the conditioning rule. Okay. Now, what we are saying is, given x3, x1 is conditionally independent of x2 given x3. You agree this is all right? This is by the traditional probability rule. So this guy here now, this basically means that p of x1 and x2 given x3 can now be factorized. Because I'm conditioning the variable, you can factorize into two pieces. This implies p of x1 given x3 times p of x2 given x3. Alright? And once that's true, therefore in that case, now you can write down what you want is this guy here. P of x2 given x1 and x3, right? Which is by definition p of x1, x2, x3 over p of x1 and x3, right? And now notice what happens. This guy, I mean basically, notice that because of this factorization over here, this thing will become equal to p of x2 given x3. x1 will simply go away because given x3, x1 does not influence x2 at all. Therefore, this distribution becomes that distribution. Okay? Otherwise, the full form is that form, where everything cancels out, you get equality on both sides. However, because assumption involved means this factorization basically, saying that given x3, these two things factorize, and therefore I can run this form. This implies this is true. Okay? Alright, so, and basically in the case of multivariate normal, you can write down, given any set of conditional independence assertions, I'm not using their language, assumptions, right, that you can write down what the implications are on the parameters of the model, and therefore what you're doing is simply, instead of full-fledged variance convergence matrix, you are simply implying that some of the parameters are basically functions of other parameters, and therefore you are not going to estimate them as if they were all fully independent parameters. Okay? There are some functional relationships among the parameters of the variance covariance matrix in a multivariate normal model. Okay? All right. So that's that for the benefit of. Okay. Once done, let's just do something we have heard before, and a lot of times. Hierarchical model, right? And Professor Mohan Delampani gave you a lecture on that application. That, I mean, you have heard the term before, you use that a whole lot, but what does it mean in terms of this simple example? Okay, so when you say x1, x2, x3 follow a hierarchical model, what you're saying is, better keep this thing over here, that, I mean, you're saying x1 given x2, x3 just depends on x2 only, all right? You have this parameter, so x3 conditioning on this guy depends only on nearest neighbor. So you have some kind of a ordering here. 1, 2, 3. On distribution x1 given both these guys depends only on, it's like a Markov model. It's a Markov assumption you're making. When you say an hierarchical model is simply saying that you can write down these variables in certain order, and then given the whole past, only the immediate past matters. Right? So this is that. This is obviously only one variable left over here. This is a marginal distribution. So essentially, you're going to join distribution in terms of these guys, just this, and that. So you can think about in a Bayesian network, you're essentially saying conditional dependencies are there, and therefore you have some kind of Markov model, not full Markov model, but at least partially Markov model. Okay. Given this, you could write down this joint distribution now. Sorry. I just right away put this notation over here, right? Without explaining what these things are. This is now, this notation basically says bracket notation here, okay? Simply says it's a joint distribution of the variable specified there. And when you conditioning say distribution this guy's over here, condition this guy's over here, okay? That's in mark and gift sampling. Anybody talk about gift sampling at all in here in the lectures? No, right? You did, right? Yeah. So gift sampling, basically, this is the standard. Avoid writing P on the extra term. Right in square brackets. This says distribution of x1 given x2, x3 is same as distribution of x1 given x2. So I should have mentioned that. So this notation simply makes you write write very little instead of writing a bit like P all over the places. Okay. So this joint distribution now is x3. You're writing this order: x3, x2 given x3, and this one. But this one is same as that one. So you get essentially you have an ordered sequence of variables, and it's saying conditioning on the full past only involves conditioning the immediate past. So it's like nothing but a Markov model. Okay, in a sense, you're specific Markov structure. So essentially, this is what you say: x3 is the marginal guy here, and x3 given x2. This is a direct arrow here, and from here you say x2 to x1. That's what this model is. This one, x1 given x2 and x3, and this model. What you're saying, this is true. So what you have essentially a model which also has not this one, but this is saying in general you have this other arrow here. X1 involves both x2 and x3, right? Parents. But this one is now missing. You end up with simply that model. Okay, so this is a very simple three-variable example. Gives an idea about what is actually being done when we try to assert certain conditional independencies in this model. Okay. Any questions about? I mean, that's the simplest. You can't use two variables only. You have to have three variables to say something about it. Okay, and that's what basically you're doing here. Start out with how to read these things out, given a network structure. What may happen. So what I will do is now go to the little general thing, and right away come back to an example which they have discussed in the paper itself. So I'm keeping them in order for Surekha, so she can. Okay, here's the general thing going on. Here's a full set of variables. First you're saying is choose some order of these variables, right? Because you say, I'm going to start conditioning x1 first, then x2 given x1, x3 given x1, x2, and so on. Some ordering of variables. And I know I can always write down this joint distribution in the form x1, x2 given x1, x3 given x1, x2, and so just that. All the paths coming in the conditioning process, right? This is always true no matter what model you have, and that you already know, all of that, you know that, right? However, what you're saying at this point, for every xi in this chain here, this is chain rule basically, in this chain, for every node, there exists some subset, pi I, which is a subset of these guys, the whole path of the xi in this sequence, right? A subset of these variables, call it pi I, such that given conditioning on pi I variables, xi and what is not in pi I. This is the complement of this set given pi I, right? So this is the not pi I part, okay, of the whole set here. So this is simply complement of this intersection, this set over here. It's saying is this variable xi is conditionally independent of whatever is not in pi I given pi I. And so that is how now you can write down therefore this distribution over here, the ith term over here in this chain, f, which is what it actually is, only depending on that, because you're saying given pi I, xi and not pi I, then x1 to xi minus 1 are conditionally independent, but this conditional probability is that point. And therefore now therefore this probability here basically becomes now simply xi, the node, given the parents. These are called parents now. These guys in pi I call the parent node of the xi node, because these guys, conditioning on these guys makes everything else, xi makes everything else conditionally independent of everything which is not in the parent node. Okay, and in this order though. The ordering is implied here because you're saying ordering of x1 to xk gives you this factorization. Alright? And therefore you can write down this pi 1 by 2 pi k, nothing but the parent node A1, parent node A2, and so on. But this is implied with this ordering here, ordering being this sequencing, because that's the sequencing we're using to factor out the full distribution into a chain rule, well chain rule, the sequence of conditional probabilities. So this is very much dependent on a sequence you use here, the order you use of variables, so that you can write down this as a function of this. And so just chain rule thing, that's what you do, okay? So you can think about the parent nodes are nothing but are basically this object over here, which says in this set on which I'm conditioning otherwise in the full chain rule, I have a subset. If I condition on that, then xi becomes independent, condition independent of everything else in this set, which is not infinite. Okay? And given that kind of thing, well, that's the idea here. Can we write down our model in a form where we only have to specify now these probabilities? Because this is for conditional subset. It may be easier to work with these guys than all these guys. Okay, because also in competitions, it's not only assess them, but when you're using competitions, basically, if you're going to specify only the subset over here, you'll have to do fewer competitions than if you will do this full chain rule thing. This may require a lot of summations, products and everything else, whereas here, some things can be ignored because they're same for every variable which is in this set over here. Can be ignored, okay? That's where the savings in competition comes, but it's as a price. Price is they're making an assumption about the model, okay? And the assumption better be the right assumption, or else it would not make any sense, because otherwise you have a model which is not necessarily correct model. And that's where statisticians, when you talk about model specification, make sure the model implied by the networks, specified network structure can somehow be verified. If not, then you just have act of faith. Okay, you have the expert said so, therefore I believe the model. But remember that all your inferences are based on that model, and if you have no way to verify it, simply at least keep in mind if something goes wrong, you have to go back and say, well, how do I correct my model, because the model implies something it didn't have, and now something else happened which was not implying my model at all. Then there was some problem in the model. Okay. Yeah.
It's like there's no unique way of writing instead of
Good. You did anticipate my next slide. Right. Yeah. This is obviously, this chain rule depends on how you order things. So either you have to search for right ordering of the variables to implement that, or you have to have some other way of doing that. And we'll come to that essentially. If n is large, if the k is large, it's going to be too many ordering, right? K factorial orderings, and you can't explore all of them. So they talk about what is an approximate way of doing that, okay? Because sometimes it's like being an expert, you have some mental picture of what affects what, okay? That's what they call this terminology cause and effect, okay? And then using that terminology, they can write down a structure which hopefully gives them the full specification. The one has to check that out, and we'll come to that, okay? Yeah, that's very true, because this is very much dependent on the ordering you put, and therefore you have too many orderings, right? Okay, so now before that point, let's just take an example which we have been discussing in the paper. It's a very toy example, but gives you some idea of what kind of thing one has to go through, okay, to set it up. So example is detecting credit card fraud. Goes away from me. Okay, I'm going to keep it here. Right? That's the example. And again, it's not example. It's not how you'll do it, because it's a very simple set of variables. To implement this kind of thing, I think about all possible other variables which you have to be included in doing this kind of problem. Okay. So variables to include in the model. Well, there could be a lot of variables to which you have to think about, but this is just a for example, telling you, let's assume that we're going to use something, variable fraud, which says yes or no, does the current purchase, is it fraudulent or not? That's all. So basically, what happens to credit card companies? You want to buy make a purchase. Before they give the stuff to you, they call up the online, some agency to go to approve the purchase. Okay. So and these people are sitting there in terminals trying to see whether they approve the purchase. Usually there's no problem. When you make a large purchase, they take a little bit more extra time, because they got to make sure you're not somebody who has stolen somebody else's credit card and trying to buy things out. Okay, so that's one variable. Second variable is gas. Now, gas purchase in the last 24 hours, yes or no? Now, what happens? Somebody stole the car. Usually, they have a stolen car too from somebody else. Okay, they're going to buy some gas from your card and go around do other fraudulent stuff. So gas means petroleum, by the way. Okay, petrol. Not okay. Gas. Gas in US. Petrol in the US is called gas. Okay, gas purchase in the last 24 hours. Jewelry. See, they want to buy things very fast from your credit card. So expensive stuff, but they need gas just to go around, commit some fraud. They have to go to different shops to buy stuff from different shops. So they need a stolen car and also need to buy, jewelry purchase. What is the variable here? Jewelry purchase in the last 24 hours. So yes or no? Those two states of that variable. Okay. Now, age of the credit card holder. But why is this relevant? Possibly because some people are very careful, other people are very not so careful, right? All right. So essentially, you can say, well, I'm going to just, for simplicity, age three groups: less than 30, 30, 50, more than 50. Okay, those are three. Discrete states. You can think about more finer gradation if you want to. Continuous variable, you can do that too. Doesn't matter. But point is that you are thinking about now to settle the problem. What are relevant variables for this problem on work at, and what are the possible states of those variables? Okay, those two, both the things at the same time. Depends if you want coarse thing, you can make it just 3. If you want more finer gradation, you can make more. Okay, now that I mentioned this term here, there's another term in engineering called quantization. Quantization is a term they use a whole lot, which simply means discretization, because continuous variable becomes discrete variable. Chop up the variable into intervals, those are quantizers. Okay. So essentially, quantization is a word which you'll hear a whole lot if you work with electrical engineers. That's simply saying, how do I make a continuous variable into discrete states, which then I use my model. Okay. So, and that why the word quantization basically, because they usually try to do is, quantize, right? A random variable. Percentiles, right? Quantiles. So essentially, what they're doing is, since I raised the issue, let me just say that because that's something you will probably hear. What we do is the following. X here is some CDF, right? F of x. And now we call it function Q of x, assume it's continuous, is simply what? Q of y as f inverse of y. So here's y. It's at this point here. This is the quantile. So this Q of y is a quantile function now. For every value of 0, 1. For 0, less than y, less than 1. You can quantile. So what they do is try to quantize a variable. So sometimes they want equally spaced points on the probability axis. So that gives them the basically give that those are the then, and then you have this over here. This becomes your, you say all these values here is one level, all these variables here are one second level, and so on. This becomes quantized variable now, discretized variable, and that's a term you'll hear a whole lot whenever you work with especially people in signal processing, because they don't want to deal with continuous variables. They don't, in the sense I said, it doesn't really matter. Use any, I'll label all these values into by one label. Okay, one level of a quantized variable, so I can work with things in a simple fashion. So, and that comes from basically quantile function. Okay, called quantized variable. So that's what we are doing here. So I'm trying to just use a continuous variable, make it quantized so that things are easy to work with. Because when you have this complete discrete network, you can use some strategies for computational large network, which are, which can handle a pretty large network. When you have continuous variable, then you have variable integration, right? Instead of summation, integration, and that introduces extra complexity in the problem. And that's why sometimes, if it doesn't matter, you can use quantized variables. If it matters, then you can say, okay, I'm going to make a finer gradation of the variable and still work with discrete variables, and not worry about trying to integrate things out in a Bayes theorem kind of thing. That takes too much time. Okay, and for the computer, things have to discretize anyway at some point or the other, okay, in some fashion. Okay, so this is for not a real model, it's simply an example. Gives you an idea of what, you could think of other measures. Sex, obviously, because probably it's a male credit card holder, and his card is being used as a fraudulent. probably the guy doesn't buy jewelry. Okay, that's why there's more likelihood of a guy. In general, they don't buy jewelry, right? More likely that if the fraudulent transaction and somebody is buying jewelry, the probability will be different than when the female credit card. That's why you think about variables which are useful for that problem. This is just 2 examples. So suppose these are only variables, right? Once you have those variables, so what's the step 1? You're simply identifying the goals of the analysis. First thing, are you going to prediction, explanation, exploration? That's very crucial, because if you, like building a model, is it for prediction purposes? Is it for basically you have already existing data, you want to explain the data or explore? You may use different techniques. So that's why you want to specify what are the goals of this analysis, how crude you want or how fine you want, and that's important to identifying many possible data sets or observations that may be useful or relevant to this problem. Okay, essentially, this is more relevant today's this day and age when you have data mining. You may have data, hard disk full of data sets available to you. How many do you want to use? What are relevant data sets? All those things become important, because here the problem is not dealing with 10 variables, trying to deal with lots of variables and lots of data. And you don't want to use all the data. So that's what you have to go through steps of trying to identify things which are relevant or useful for this problem. Okay? You can always expand that analysis. You can have more data you left out. You can always include that through the Bayes theorem again, Bayes process again. But you want to make things simple, okay, in general first. Okay, determine what subset of these variables have to be included in the model. What's what? Organize the observations into variables having mutually exclusive and exhaustive sets. Like we said, for each variable, but what are the states we are going to define? The age with three possible levels, right? So essentially, when you've done that, you have done like step 1, that here is a set of variables you're going to look in your model. Okay, when done that, what are the tools now for all this? You need tools are basically Bayesian learning. Assessment is what you need to know how to do probability assessment in this guy, Bayes theorem. This and that has to be the tool which you always need all the time for this kind of process. Okay, so this is the most important step in it. Just like if you don't have all the relevant variables, the model will be incomplete. It won't be a very good model. That's why you need to spend a lot of energy on this. Once you've done that, other things might become much. Next step is the structure of the network. Computation becomes a more automatic step than it is. Okay. Okay. So now you have to build a directed acyclic graph encoding these conditional independence assertions. I still always add the word assumptions, because somehow that's my own training, and those are not assertions I can make. If you want to make assertions, they better be coming from the expert and not a statistician. Remember that. You can't make assumptions for the subject matter guy. It's something, the assumptions have to be made by them and not by the statistician in general. Okay. So here's a simple example now. What are we going to do? I'm going to do the network first and say what are the assumptions involved there. Here's what you need is, for example, this 5 variables, 1, 2, 3, 4, 5, fraud, age, sex, class, and jewelry. Right? Those are variables you specify in your to example. You're saying is, in this case, what you're saying is, in this barrows, the fraud is the fraudulent transaction likely to affect jewelry purchase. So this is the cause, this is the effect. Okay? Arrows go from cause to effect. Now cause taken very loosely, okay, again, right? So if fraud is the cause of this transaction, this may happen. This may happen too. Person may buy gas if fraud is the cause. Okay, so this is the effect. Is the arrows go from cause to effect in that terminology. Okay, age, again, jewelry. This is the age of the credit card holder, right? What is happening is age and sex both. This is what saying is, somehow people in different age groups may have maybe a little bit less careful about keeping their card properly. People who are in this middle age group, they are pretty good about that. Okay, and the younger guys, they don't care, and the older guys, it's part of age now. Male, female, this thing again. So you put this. We'll talk about what the corresponding statements here are. But this is the kind of. Some person says, this is my network now. Here, all the nodes from each node, the parent node the cause to effect errors, and then we read it out. Once you have this model, then you're also saying for each node, now you need to write down what you need to write down. Here you're saying is fraud. What is the probability of fraud in general? But there's no parent node here, right? There's no condition required. So this is a node which has no parents at all. Therefore, it's the marginal probability here. There's no parent here either, right? So there's a probability of age. Basically, what are the age group people are below 30? What percent of people are in that age group who have credit cards, right? From this company. Same thing for second middle age group, and third one is not specified here because third one is more than 50, which is like at the probability itself. Third one is should be there, but they don't need to specify. I mean, this is enough. Third is specified. What proportion of people are, the credit card holder male or female? About 50-50, at least in the US it may be true, but other places may not be. Okay, and then so what are you seeing here? Every node at this node, what is parent here? This parent, right? At this node, probability gas equal to yes, given fraud equal to yes. That's the probability specified probability. Here, that's the probability here. So given all values of this node here, parent node, G equal to yes, F equal to no. Other is not. What is missing here in this specification? G equal to no, F equal to yes, right? But then you can get that automatically because the G is taking two values yes and no. If you specify F equal to yes and this conditioning, this probability, other is 0.8. So I'm not doing it now, but they're already there, part of the implied by the probabilistic calculation. Okay? In this case, this guy has three nodes here. Right? Three nodes here, two values here, three here, two here. So 2 times 3 times 2 is what? 12 possible combinations of these parent nodes. That's called configuration. The parent nodes for this node take 12 possible configurations because you have 2 here possibilities, 3 here, 2 here. Multiplication rules also 12 possible configurations. So to specify probability of this here happening for all those configurations. Okay. Well, so what do you have? Well, this says here probability J equal to yes. Given that there was a fraud in the some based on experience, and this star is used like A equal to star, S equal to star. It says no matter what age and sex is of the person, credit card holder, whenever there's a fraud, this probability is 0.05. So this says for every value of age and sex here, when F is yes, this is a problem. That's what it's saying. So this is same for all possible 4 combinations of this age and sex. No, 6 combinations here. This is same. Now what about J equal to no? That they can compute automatically because we know from J equal to yes, given this conditioning, J equal to no, they have to add up to 1 given this conditioning, right? So that's now J equal to yes, given F equal to no. So S is yes, then no value. No, there are all no's here from then. F equal to yes, you're simply saying it doesn't matter what combination you choose, the same probability. That's what you're asserting. Otherwise, you have to specify all other combinations here too. In this case, age is less than 30 and sex is male, this probability. So these are configurations here. 1, 2, 3 here. These 3 are same thing as before, except I'm changing these 3 age levels. Sex becomes female here. Everything else exactly these 3 combinations here. So essentially you have to specify for every node here these conditional probabilities for every parent configuration. Now remember that if this was not there, for this one you need also this variable here too, right? It becomes 12, we have 24 nodes. You don't have, because of a model, you're saying it, I need to worry about only the parent nodes here and only specify the probabilities for all because these are called local probabilities. So every node has local probabilities, which is simply probability of this variable taking certain value for conditional every possible configuration of the parent nodes. Okay? And once you have done that, basically, we're using the ordering here was specified F, A, S, G, and fraud, age, sex, gender, gas, and jewelry. This is the order you use to specify that. Okay. Now, what's happening? The R's here are from cause to effect. This is a cause, this is effect. That quote unquote cause, quote unquote effect. Okay. A star is simply shortened for any value. The same for every value of this combination is same probability, and these are called the local probabilities. Okay, so once you specify these, then you can write down now all possible joint probabilities in this framework. So basically, this is a way of thinking, of trying to organize your thought process so that you can write down these conditional probabilities in an easy fashion and also assert whatever assumptions you're making in the model. Okay. Well, time is really flying by fast. Let's just do the following. Here's my model, right? What are the possible assumptions here? I'm going to doesn't work. Okay. I'll go back and forth. So first thing you're saying is probability A given F is probability of A. F is basically you're saying F and A are. Why is that? Because given F, notice that age here is the ordering here is this F A S G J, right? This is ordering. So I'm going to marginalize this one first. F is the first one variable. Age is second variable. Age given F, right? What I'm saying is age given F probability same as probability A because this is no arc from here to here, right? And therefore this probability is same for every level of prior, and therefore I'm asserting that F is conditional independent of A. At this point, there's no conditioning here, so F is independent of A in this one. Okay, that's the assertion because there's no arrow here. Otherwise, there's an arrow in this ordering here. It's missing. Therefore, this is the first assumption. Second is S given F and A. What happened here? This guy, there's no arrow here, right? Or there's no arrow here. It says in this ordering, S given these two guys really is same for every possible combination. Where therefore, S is independent of F and A. All right, that's the second assumption you're making, because these arcs are missing. Okay. Third assumption is G. Now this third variable is G here. You have F A S G now, and this G here you're saying G given F A S is same G given F because this says G given F A and S. These three variables on the first layer here. These two guys, there's no arrows here. Therefore, this condition probability is same as G given F. And so which says given F. G and A and S on this set here, what happened? You identify the set A and S here, this subset over here, this subset over here, which was saying that in this subset here, A and S is subset, so that G is conditional given A and S given F. So if I choose that, this is your pi I now. This is your pi I, pi G. Pi G with this is parent node here because saying given F, the subset pi I is that, and therefore given everything which is not in the subset, this set FAS, F is pi I. This is the part which is the complement part, and this become condition independent given F. The last one is FAS, all these guys here, and this is the same as saying J is jewelry here. This given all the variables in this subset, you're saying this only depends on FAS because these are the arcs coming to that node, and this does not affect this guy. So. And that's what it's saying. G is conditional independent jewelry variable given F and S. So now you have to specify for jewelry only all configurations which correspond to all possible variables from which the parent variables from which these arcs are coming. Okay. That's once you understand that stuff, you can do a whole lot of that stuff very easily. But that's the assumption. So essentially, when you write down this kind of network, you are making this kind of assumption. Okay. And obviously, you have to know subject matter before you can assert these. As a statistician or econometrician, your job is to help somebody else analyze the data or model the data, not just model the data for them. You can't model you can't specify their model in some sense, unless you are also playing the two roles, subject matter expert and the statistician at the same time. Okay, you have to keep those roles separate in your mind. If you don't do that, then there is always a danger involved. Okay, so like you said, that means I have to worry about what ordering to choose, and then sometimes different ordering will be different model. Okay, okay. In this problem, if I use the ordering J, G, S, A, and F, the different ordering, you get all this. That everything is connected to everything else because you just use the different. So therefore, sometimes what they say, what do we do? This ordering gives you this model, which says there's no conditional independent at this point because I didn't use specific ordering. Whereas this model, things become simple. So that's where they say, well, what do we do? Obviously, sometimes it's very difficult to look at all possible and k factorial orderings over here. Okay, so what is the what's the way out? You want things which can work and essentially not worry about. Because the problem is very difficult to really explore all possible orderings, here's the way out. This is one of the engineering solutions of the problem, okay? Well, construct the network without any ordering. How do we do that? Okay. Usually they say, the decision maker can often readily assert this relationship between variables. Knowing the variable what they are, you can say, well, oh, if it's gas and jewelry, I know that these things won't win. Once it's a given f, they will be independent. That's a kind of assumption you're making by knowing what the variables are. Okay. So when you need to, for every node, what are the immediate causes? So you can put the arc there, okay? And that is, again, expert knowledge, not something statistical model specifications and so on. So this usually that can happen. And then also this thing about what is the cause of a node and what are the immediate causes, basically. This thing can be done by somebody who knows the subject matter, all right? And so what it does is it writes the variables out, say, here's the cause, here are the immediate effects of that cause, okay? Like in this case, if you think of this model here, if you ignore the ordering, the model we just had a minute ago, what happened, Mike? Yeah. You can say, well, are my 5 variables, I'm going to assert that these things are independent. Not worrying about ordering anymore, these things are independent, okay? So, and for this node, this being cause, this is the cause, these are possible immediate effects of that. This is the cause, this is possible. I mean, age and gas don't get related, but jewelry is something which might. So this is, once you do that, there's no guarantee that once you have given all the arcs, whatever you have, that you really have fully specified model. So one has to check it out. So that's usually what comes in. Usually you do the arcing and then say, oh, is the right, does it really fully specify the full joint distribution or not? If it does not, then you have to, basically you go through some kind of iterative process before you can, if you don't want to, but you really can't explore all possible ordering, so you do this process in almost all cases. This is the usual engineering language says this, it results in network structure defines, has to be checked, does it doing it or not, okay? And essentially once you do that, what are the, write down the conditional independence statements now, does it really make sense or not, okay? Or something, do I need to modify my network? So at this point, when you do without any ordering in mind, then you really have to check your network structure out. Otherwise, there'll be problems. Okay. Now, the step is then you assess the local probabilities. That's the probability I wrote down. You have to assess those once you have a network, because those are the only probabilities you need to know to get probabilities for any other specification of any kind. From that, then you can write down the full joint distribution and you can compute any probability you want to. Okay. So building this is a basically iterative process, because you have to go back and forth, check your model out, what the assumptions are, do they make any sense or not modify your model, okay? So you can do one step basically. What do we make inference in Bayesian networks? That's something which is, what it means in our language is the following. Given a network, which is based on prior knowledge, data, combination of, need to determine various probability of interest from a model. So basically, I suppose I want probability of fraud given some configuration of this variable, which by base term we can write it down. But the thing is, this is a simple model, you can compute this easily, but in a large model, there's will be too many configurations over here, and to compute these guys out, we have too many sums involved over here, and that's where you use the stated conditional independence assumption you have made in your model to minimize computations in here. Okay, because this is the full specification over here, but in this case, because of the model assumption you have, you don't necessarily have to go to all possible configurations over here. You can minimize that, and that's where these people talk about automatic computational algorithms for a given network, and usually large network, and there are algorithms available. They use the stated or asserted conditional independence or reversed. Reversed. They call arc reversal, which is nothing but you have A given B probability, you want to compute probability B given A, right? That by Bayes' theorem. and that's called arc reversal. We have a network, have an arc going this direction, another direction, I have to use Bayes' theorem at that local level. And that's what people call them, people in AI call it arc reversal, but nothing but local computation for Bayes' theorem, so they can go from the reverse direction from here, okay? If all variables are discrete, the algorithms available which are used right now, these are all, I did not give the names of other people, these are statisticians, Lurston, Spiegelhalter, Jensen, David, these guys have algorithms available which are now being used in this area very much for large networks, but then they simply, they understand, these guys understand the conditional difference much more than the people in computer science, okay? So they can write down how do I use all the underlying conditional independence assumptions I have made to compute the things I have to do in a fast way. So the algorithms which are being used today for the multivariate Gaussian are Gaussian mixtures models. Lurston has a paper available which talks about how do you handle this kind of models in a quick fashion, large dimension model, okay? Approximate methods for inference based on generalized linear models. They have that available. So basically, for class of processes, if you write down a model, how do I compute them? Then they can be used as modules in a larger network. Okay? That's what they're trying to build over time now. Of course, we can say, well, you know what MCMC is. You can do that too. MCMC is still approximate because when you do simulation from the posterior distribution, you have to summarize that data, which introduces some approximations in the summarization basically. Therefore, with a large number of variables, basically, it takes a lot more time. And what you need to do is try to combine MCMC, even in MCMC, if you have, instead of all four conditionals, if you know there are some conditional independence available, you can reduce the effort in MCMC also, right? And that's what these algorithms are basically people working on for a class of models. What are the computation involved? So I can just now specify how many nodes on each variable, how many levels, and things of that sort, and then you can use a package program to do that. That's programs available. This paper mentions a list of programs which are basically some commercial, some freebies available, and you can download them freebies and use them for 2 examples. If you want to, be working for a big company, they better pay money for that, for the big software package available for that. So this is like a very minimal introduction to the topic. The paper has a lot more. It talks about details about if I had missing data, or if I had other regression problem, classification problem, how do I implement the details are basically how do I reduce the effort in solving those problems. They're all given there, and one can read them very easily, and then the references are fairly comprehensive list of references in the paper, which takes you about details for all those things in general. I'm going to stop at that point, okay?